Swayam Prabha. Digital India. Educated India.
Welcome to this lecture number 10. So, we are continuing with the previous lecture. So, wherein we went for we derived an expression for the two-dimensional general groundwater flow equation for an isotropic aquifer. So, which is of the form d square h by dx square plus d square h by dy square is equal to s by t into dh by dt, where here h represents the head, x and y represents the flow directions, s is the storativity, t is the transmissivity, and since that is an isotropic aquifer, the transmissivity in both the directions Tx and Ty are same, equal to T, and this dH represents the rate of change of head with time, the partial derivative of the rate of change of head with time. Suppose it is a three-dimensional flow and the flow in the aquifer is isotropic. So, in this case there will be the third term also, okay, and so therefore, this for an isotropic aquifer, the general 3D groundwater flow equation will be d square h by dx square plus d square h by dy square plus d square h by dz square is equal to s by t into dh by dt. So, this is the expression, and obviously in this case the left hand side is denoted by del square h. So, which is the combined notation for these three second order partial derivative terms in with respect to each of the directions, and so this is when the flow is unsteady flow. So, this is of the form, this is known as the diffusion equation, and when the flow is steady, then this dH by dt will become 0. So, that the right hand side will be 0, and then this equation attains the form of the Laplace equation. Okay, so, when the groundwater flow is steady, in that case this dH by dt is equal to 0. So, therefore, d square h by dx square plus d square h by dy square plus d square z by d square h by dz square is equal to 0, and obviously, so this is del square of h So, del square H, which is equal to d square H by dx square plus d square H by dy square plus d square H by dz square, which is equal to 0. So, this is the famous Laplace equation, and so this is the general groundwater flow equation, general 3D three-dimensional groundwater flow equation here we can add one more, this one 3D groundwater steady flow equation for an isotropic aquifer. So, initially when the aquifer was anisotropic, in that case it will be different, okay, this the terms will be different. So, for anisotropic aquifer, the 3D groundwater steady flow equation will be kx into d square h by dx square plus ky into d square h by dy square plus kz into d square h by dz square, this is equal to 0. So, this is when the flow is steady and the aquifer is anisotropic, and the flow is steady and three dimensional, and when the flow is anisotropic, three dimensional through an anisotropic aquifer, and the flow is unsteady, in that case there will be the right hand term, the right hand side will not be 0. So, here I can write down, say, for unsteady flow, the 3D general groundwater flow equation through an anisotropic aquifer will be this kx into b into d square h by dx square plus ky into b into d square h by dy square plus kz into b d square h by dz square. So, this is equal to S into dH by dt. So, this is the expression here. The flow is unsteady and three dimensional, and the aquifer is anisotropic. So, in that case this is the general form, and when the flow becomes steady, the right hand side term becomes 0, and the aquifer is isotropic, in that case Kx is equal to Ky is equal to Kz. In that case it will be the Laplace equation. So, therefore, so this is how the general groundwater flow equation it varies. Now, the same expression the for say in radial coordinates, that is axis symmetric groundwater flow. So, the axis symmetric groundwater flow through an isotropic aquifer the equation will be the groundwater flow equation will be d square h by dr square plus 1 by r dh by dr, this is equal to s by t into dh by dt. So, this is the in the cylindrical coordinate this one or the radial coordinates, where r is the radial distance and h is the head and the radial coordinate, and obviously this s is the same storativity or storage coefficient, t is the transmissivity. So, and the flow is unsteady. So, here groundwater unsteady flow. So, and the axis symmetric groundwater steady flow, and the equation for axis symmetric groundwater steady flow through an isotropic aquifer is d square h by dr square plus 1 by r dh by dr, this is equal to 0. In this case the flow is steady. So, therefore, this dh by dt, this term becomes 0. So, the right hand side becomes 0. So, this is the obviously the Laplace equation, its equivalent in the cylindrical coordinate system or the radial coordinate system. So, now let us consider say this is the confined groundwater flow between two water bodies. So, here let us say this is the upstream water body, so let this be x, and this is x is equal to 0, and here we have the so this is the water level at the upstream water body where the head is h 0, and of course here we have the top and bottom confining layers, that is the impervious layers of this confined aquifer having a thickness b, and so here this is the downstream water body where the head is h 1. So, this is the here this is the upstream water body. So, this is the downstream water body, and the flow is taking place between one, and here let us say, so this is the general the ground between these two is one, and obviously, so this is how the groundwater flow takes place, and so this is the hydraulic grade line, okay, and so this is the downstream water body, this is the upstream water body, and so in this case obviously consider steady flow through an isotropic aquifer, and in this case this is the flow is one dimensional. Okay. So, therefore, the governing equation will be d square h by dx square is equal to 0, because the flow is only in the x direction. So, therefore, the this d square h by dy square as well as d square h by dz square. So, they will be 0. So, only we get this is d square h by dx square is equal to 0. So, this is the governing equation. So, on integration, we get, so this is h which is equal to say C 1 x plus C 2, okay. And now we need to substitute the boundary conditions to evaluate this C 1, the constants of integration C 1 and C 2. So, the boundary conditions are at x is equal to 0, h is equal to h 0. So, therefore, h 0 is equal to C 2. And the second boundary condition is at x is equal to L. I am sorry, here I just forgot to show this as one. So, this is x is equal to L. So, this is the distance between the upstream water body and the downstream water body. So, here at x is equal to L, then h is equal to h 1. So, this when C 2 is equal to h 0. So, therefore, we get the expression that is x is equal to, I am sorry, this h is equal to C1x plus H0. Now, let us substitute the second boundary condition. So, this therefore, H1 will be equal to C1 into L plus H0. Therefore, C1 is equal to H1 minus H0 divided by L, which we can also write this as minus of H0 minus H1 divided by L. Since H0 is bigger, the head in the piezometric surface in the upstream water body. So, it is having this one. So, we can write that if we write that first. So, therefore, we get the expression after evaluating both the constants, we get this H is equal to H0 minus H0 minus H1 by L into X. So, this is the expression for head at any general section, which is at a distance of x from the upstream water body. And so this is the, here you can say this is the equation for, so this is the equation for the hydraulic grade line HGL, which is assumed to be linear. Okay. And let us also write down an expression for the discharge per unit width of the through the confined aquifer between two water bodies. So, the by Darcy's law, discharge per unit width for groundwater flow between here you can say the confined groundwater flow between two water bodies is given by this Q is equal to minus the hydraulic conductivity K into dH by dx, K into minus dH by dx, where this minus dH by dx is the hydraulic gradient, into the area, since this is unit width. So, this will be 1 into B or simply B. Okay. So, in this case, so this is minus K into B into the hydraulic gradient is minus of H0 minus H1 divided by L. That is, Q is equal to K into B into H0 minus H1 divided by L. So, this is the expression for discharge per unit width for confined groundwater flow between two water bodies. So, the discharge per unit width for confined groundwater flow between two water bodies, and obviously, so here this we all start with this steady flow, confined groundwater steady flow between two water bodies. So, in this case the discharge per unit width is given by is K into B, which we can also replace this by transmissivity T, the transmissivity or transmissibility. And H0 and H1 are the heads in the upstream and downstream water body, and L is the distance along the flow direction between the two water bodies. So, if you know the transmissivity or the hydraulic conductivity and the thickness of the confined aquifer through which the flow takes place between the two water bodies, the upstream water body having a head of H0 and the downstream water body having a head of H1, and with a distance of L separating them. So, then this Q is given by K into B into H0 minus H1 divided by L. Okay. So, now let us come to the unconfined flow, that means flow through an unconfined aquifer, wherein the Dupuit's assumptions for unconfined groundwater flow. So, in 1863, so these Dupuit's assumptions, Dupuit is an hydraulic engineer, and in the year 1863 he proposed two assumptions for the unconfined groundwater flow. The first assumption is the curvature of the free surface is very small, so that the streamlines are assumed to be horizontal at all sections, So, this is the first assumption, and as per this assumption, even though there is slight inclination for the streamlines, so that inclination is neglected and the streamlines are assumed to be horizontal at all sections. And the second assumption is the slope of the hydraulic grade line that is HEL is equal to the free surface slope and it does not vary with the depth. So, this is a second Dupuit's assumption. The first assumption, in which the streamlines are assumed to be horizontal in all directions. So, that whatever little inclination in the streamlines is there, that is neglected. And the second assumption is the slope of the hydraulic grade line is equal to the free surface slope and it does not vary with the depth. So, these are the two Dupuit's assumptions, and which are applicable for groundwater flow through unconfined aquifers. And now, using these Dupuit's assumptions, let us determine the groundwater flow through unconfined aquifer. So, here let us consider the groundwater flow through unconfined aquifer. So, let us consider this as the z direction, this is the x direction, and this is the y direction, and here let us consider so this is the water table, and so this dimension along the y direction so this is delta y and this is the origin and this dimension. So, this is delta x and this head is h, and here let us consider the groundwater inflow. Let us consider the flow to be in the positive direction of x and y. So, let this be mx1 and the groundwater outflow, the mass outflow, let us take this to be mx2 in the x and y direction. Similarly, the groundwater inflow in the y direction, let us take this to be my1 and the groundwater outflow through the other phase in the y direction, let us take this to be my2, and this is the water table. So, now let us write down the expressions for the mass flux entering the element So, this is given by mx1. So, this is rho into say Vx, which is the velocity, groundwater flow velocity in the x direction, into h into delta y. H into delta y is the cross sectional area. So, this Vx into the cross sectional area of flow, that will be discharge into rho, that will be the mass flux or the mass rate of flow, mass rate of inflow. Similarly, mass flux leaving the element. So, this is mx2. So, this is given by rho Vx h delta y plus let us add the mass rate of change term in the x direction, that is d by dx of rho Vx h delta y into this delta x. Okay. So, therefore, now let us write down this is the net mass efflux in x direction So, this is mx1 minus mx2. So, this will be given by minus d by dx of rho Vx h delta y into delta x. Similarly, net mass efflux in y direction. So, this is given by my1 minus my2. So, this will be given by minus d by dy of rho Vy into h dx h I am sorry h delta x into delta y. So, therefore, since there is neither inflow nor outflow in the z direction, so the continuity equation gives obviously. So, here this mx1 minus mx2 is denoted by this is delta mx. Similarly, my1 minus my2 is denoted by delta my. So, therefore, this delta mx plus delta my plus delta my is equal to 0. Therefore, we get, so after simplification, we get d by dx of Vx into h plus d by dy of Vy into h is equal to 0, and obviously. So, here this delta x delta y as well as rho, okay, so that can be cancelled. Okay, so, this is the expression we get, and we know that say by Darcy's law we get this Vx is equal to minus k into dh by dx and this V y is equal to minus k into dH by dy. Therefore, if I call this equation 1, so this equation 1 becomes d by dx of minus k dH by dx into h plus d by dy of minus k into dH by dy into h, this is equal to 0. And again here you can take out this k outside the one, can cancel out. So, therefore, we are left with this is d square by dx square of h square plus d square by dy square of h square is equal to 0, and this you can denote this as del square of h square. So, this is the governing equation for steady groundwater flow through unconfined aquifer. Unconfined aquifer. So, this unconfined aquifer for the steady flow, this it satisfies Laplace equation in h square, whereas the confined aquifer will satisfy the Laplace equation in h, while in case of unconfined aquifer it satisfies the Laplace equation in h square. So, now let us consider the unconfined aquifer, that is the unconfined groundwater steady flow with recharge. Suppose there is some recharge in the z direction, say when there is due to rainfall or precipitation. So, this the groundwater is getting recharged. So, in that case what will be the expression, let us see. And so, here let us draw the basic figure with x, y and z directions, and so this is the water table, and it is getting a recharge at the rate of r, and here, so this is the origin, and this is the dimension in the x direction, and this is the dimension in the of this element in the y direction, that is delta y, and the variable head h, and in this case So, let this the mass inflow through x direction, let it be mx1, the mass inflow, let this be mx2, and similarly the mass inflow in the y direction, let it be my1, and the mass inflow in the y direction, mass outflow along the y direction be my2. And obviously, so this is the water table. And this R is the recharge in the z direction. So, now in this case it is all similar to the previous case, except that in this case, so there will be an additional term, that is mass efflux in the z direction, that is the net mass efflux in z direction, that is delta mz, is given by rho into r, which is the rate of recharge, into the area of flow perpendicular to the z direction, that will be delta x into delta y. Okay. So, therefore, for steady incompressible flow, the continuity equation becomes delta mx plus delta my plus delta mz is equal to 0. So, that is we get minus d by dx of rho Vx h delta x delta y minus d by dy of rho Vy h delta x delta y, and this recharge, that is the net efflux in the z direction, that is given by rho r delta x delta y. This becomes 0. So, again let us substitute Vx is equal to minus k into dh by dx, and Vy is equal to minus k into dh by dy, and simplify. So, here we get this is of course, here this is rho delta x delta y that can be taken out, and in this case we are left with, that is d square by dx square of h square plus d square by dy square of h square. This is equal to minus 2r by k. So, here this term r is there. So, therefore, it will be h square by 2, and then so it will be minus 2 r by k. So, this is the general groundwater steady flow equation through unconfined aquifer with recharge. Okay. So, the general groundwater so here this is the governing equation. So, in case of steady flow through an unconfined aquifer, it satisfies Laplace equation in h square, whereas when there is a recharge through the this one, the unconfined aquifer at the rate of r along the z direction, the general governing equation for steady flow through unconfined aquifer will be given by this is d square by dx square of h square plus d square by dy square of h square. So, this is equal to minus 2 r by k. Okay. So, this is how the groundwater governing flow equation, it changes its form in case of an unconfined aquifer when there is no recharge as well as when there is recharge. Now, let us consider the one dimensional Dupuit's flow with recharge between say two water bodies. So, let us say this is a 1D groundwater flow between two water bodies groundwater unconfined flow. With recharge. So, let us consider unconfined groundwater flow, and let this be the upstream water body. And let this be the ground surface, and let this be, so this is the upstream water body, where the head is h 0, and downstream water body where the head is h 1, and there is the constant recharge, and here this is the constant recharge of rate r, and in this case the water table will assume a shape like this. There will be a peak somewhere in between, and wherein the H is HM or the H max, and this is the water table. And so, the aquifer permeability is or hydraulic conductivity as K, and in this case there is a obviously flow into the upstream water body as well as flow into the downstream water body. This is Q 0, this is Q 1. Okay, and in the next lecture, and obviously at this so at any general section H, say here this is the general section H. So, this is x is equal to 0, x is equal to L, and so obviously this is L, and at general section H. So, in this case this is Q x. So, in the next lecture we will discuss this one. Thank you.